Hey, Honors Physics, this is Mr. Hausman. We're going to take a look at page 28 in the energy unit, the energy work and power unit, for the introduction to a brand new principle related to energy and work, and that's power. So I bet almost every single one of us have heard the word power. We refer to things that are powerful as like big machines. In one of my classes today, they've already talked about how airplane engines, right, are considered very powerful. And other things that are powerful include like the engines of a large boat, like a cruise ship or an aircraft carrier. Also, sports cars, right? Cars have power. Certain cars are more powerful than others, and generally those are the sports cars. But also, don't forget that large trucks are considered to be powerful, and we'll try to figure out what they have in common. Now, where else might you have heard of power besides transportation or moving things? Well, maybe you are familiar with powerful speakers. And I mean speaker sound systems, not like a profound public speaker or an influential speaker, but a powerful speaker like at a concert. Or maybe a bright laser beam. All of these have something in common, and what it has to do with is how quickly work or energy is transformed or used to do something. So the fundamental definition that these all have in common is that power is a rate at which work gets done. Or in the case of maybe a sound system, it's the rate at which energy is transformed. But we'll be using the work definition, the rate at which work gets done. Another way of thinking of this is it's a simple ratio, work divided by time. So let's set that up as a ratio, work measured in joules divided by time measured in seconds. Now, when you're done with a calculation of work divided by time, you get a brand new unit. What is a joule divided by a second? 1 joule of work done in 1 second is equal to 1 watt of power. And it kind of includes the work and the time unit. So when you think about a light bulb being 40 watts, a 40-watt light bulb is really using 40 watts, is really using 40 joules every second. So the louder the sound system, the brighter the light bulb, or the more powerful maybe the engine, the more energy it's using per second. And what we want to connect that to is that, remember, what work has to do with. Work is a force, right, that changes the mechanical energy of a system. You push it and you move it, so therefore you're giving it kinetic energy, or maybe you lift it and give it potential energy. But you're fundamentally applying a force on a mass, and it's causing it to change the energy of it. So most of the time, we do work at a nice steady pace. Our lives are busy, we have a lot to do, and sometimes you find yourself kind of putting in an even workload. Other times, you try to get work done very quickly. And this could be academic work, or it could be maybe a workout. Well, if you do a lot of work in a short amount of time, we would consider that, right, kind of more powerful. So in this example, 2 identical people that do the same work, and one of them climbs a hill in much less time than the other. So let's kind of compare these. This is hiker A and hiker B. And the person who, they're the same size person, so their work is the same, and we'll figure out why that's true, right? Divided by the person who does it in a short amount of time versus the hiker who does it in a large amount of time. And I want you to kind of notice that I made the T larger to imply that it, of course, took more time. It's a conceptual way of describing kind of this quantity. Now, how do we know that they did the same work? Well, they applied the same force. They lifted their body weight. They climbed the same mountain, so their weight and the distance up the hill is the same, or the height up the hill. So again, force times distance is the same. So what you get when you divide by a smaller time is you get a larger power rating. or rate of which work is done. Whereas for hiker B, the power is smaller because they took more time to do it. So that's usually how we compare the rate at which work is done, and we almost always consider that if you have the same amount of work to do you do it in less time or do you do it in more time? Well, the smaller the time, the more powerful the system must be. So like a motor or an athlete, right? If they want to do more work in less time, they need to be quicker about it. Okay, so let's do a really simple setup problem involving a squirrel. And he's a little squirrel, and we'll make him a red squirrel. And this is not at all what a squirrel looks like, but we'll at least give him, a tail. And he's doing a push-up. I saw this funny meme recently of a squirrel laying flat on the pavement. I've actually seen that in real life on really hot weather. Squirrels will actually lay down on cool rocks to cool down their body. And let's say he decides to do a little workout. So he's 1 kilogram of mass. He lifts himself by 5 centimeters, which is 0.05 meters. So his distance that he lifts himself. And it says that he did a 0.5 joules of work, but let's actually confirm that. Work is equal to force times distance. But let's draw a quick free body diagram. What force is he exerting? Well, he has an applied force that's causing him to rise up in the air. He has a body weight, but those two forces are equal and opposite. So we'll basically just say that his applied force is equal to m times g, the same formula for the force of gravity. And what distance did he move himself? 0.05 meters. So 1 kilogram times 9.8 meters per second squared, the gravitational field of the Earth, and then he moves himself against that field 0.05 meters. And that comes out to be 0.5 joules. So that's if he does one push-up. He's done very little amount of work. But the question really is, well, how powerful is the squirrel? Well, they're probably not considered a very powerful animal, and let's prove that. You take the work he did doing a little push-up, divide it by time, 0.5 joules, and according to the narrative, it takes him 2 seconds to do it. He's taken his time. So you get 0.25 watts. Pretty small, right? Not even a very bright light bulb. Right, so that amount of energy for those 2 seconds. So he was doing during those 2 seconds, but then he stopped. So power is the rate at which you do the work, but it ends as soon as the work is over. Okay, let's go to the bottom of this page, and let's take a look at more like a full-size human body doing some work. So now here's a student who's doing a pull-up, a chin-up. So here's the bar, and here's the student. And they're going to lift their body weight up on that bar, so doing a chin-up. So the center of that person's mass, or their belly button or their chin, rises a total height of 0.25 meters. So that's my distance vertically, or height. The mass of this person is 42 kilograms, so much larger than a squirrel. And in terms of free bodies, again, the applied force, the lifting force, is equal and opposite to his weight. So if someone said, find the work done to counteract the force of gravity, it's the applied force times distance, or his body weight times how far did he lift himself. And he only did 1 repetition, according to this. So now 42 times 9.8 times a distance of 0.25 meters, 25 centimeters, so much farther than the squirrel did, which was only 0.05 meters. And that comes out to be 102.9 joules. And if you go and try that now to calculate his power, work over time, it's nothing more than 102.9 joules over 2 seconds. So apparently, because it's the same time as the squirrel, we can kind of compare, well, the squirrel is lifting a much smaller body weight, doing less work, but he's doing it in the same time. What you notice is that the power rating, when you divide that out, comes out to be 51.4 watts. So is that a powerful person? Well, yeah, of course they're more powerful than the squirrel is, and the person's biceps, and actually for those of you who know fitness, it's actually also back muscles that allow you to do a pull-up or a chin-up. Now, is that the greatest amount of power a human can generate? No, far from it. In fact, I have seen power ratings of students climbing stairs that's upwards of 1,000 watts for a short amount of time, maybe 4 or 5 seconds at a time, and they were able to generate 1,000 watts. Can they do it for minutes on end? Well, professional cyclists who have incredibly efficient energy output, and maybe when they're climbing mountains, especially in European cycling, they often maintain power outputs of 400, 600, 800 watts for minutes at a time, 10 or 20 minutes. Sometimes they're leading the pack and they have to push ahead. Sometimes they fall back into what's called the peloton. But it's not uncommon for a human athlete, a trained athlete, to get into the hundreds, if not break 1,000 watts for some period of time. So that's an introduction to power, mechanical power, dealing with lifting some objects. It could be really any work done on any object divided by its time.